Hi everyone, welcome back to K Science Academy. It has been a long time. So in today's video, we are going to talk about dimension of physical quantities, both the fundamental quantities and the derived quantities. So don't forget, we have 7 most important fundamental quantities and we have several derived quantities. So in this video, we are going to talk about the dimension of both the physical quantities, both the fundamental quantities and the derived quantity, in which both are called physical quantities. That is, physical quantities can be subdivided into fundamental quantities and derived quantity. So we are going to talk about dimensions of all these physical quantities. Okay, here are the 7 fundamental quantities together with their units and their dimension. Now, one thing about dimension is that we pick the first letter of the fundamental quantity, we write it in uppercase, and that will be our dimension, but not true for the 7 fundamental quantities. It is only true for the most important one, which is mass, length and time. These are the 3 basic quantity, but we have 7 fundamental quantities, but these are the most common one, these first 3. Now, the uppercase of the first letter here is M, and that's the dimension of mass. Look at time, that is T. Length, that is L. But when we get to temperature, temperature is measured in Kelvin. So we don't use T because we have already used T for time. So we use theta. Why some people use K, uppercase K, but this is more common. Now for current, current is measured in ampere. So we don't use C for current, we use A. The first letter of ampere, we use it in uppercase, while some people use capital I, but I prefer A. Then for luminous intensity, which is measured in candela, we use J for this dimension of luminous intensity. Then for amount of substance, which is measured in mole, we use N, that is number of mole, we use uppercase N to denote the dimension. So these are the dimensions of the 7 fundamental quantity, which is mass, time, length, temperature, current, luminous intensity and number of mole. So now here we are asked to find the dimension of the following quantities. Now the quantities are force, momentum, Young modulus and gravitational constant G. So there is not going to be any problem in solving this. One thing I just want you to know is that for us to get the dimension of any derived quantity, because if you look at all these quantities, they are derived quantities. So since they are derived quantities, what we can do is to simplify them, write a formula for them. The first thing you need in finding the dimension of derived quantity is to write the formula. Write the formula in terms of the fundamental quantities, then you can go on to find the dimension. Now looking at the first one, we have force, which is mass times acceleration. And don't forget, for mass, the dimension of mass is capital M, right? Now acceleration is the same thing as velocity over time, where the dimension of velocity is distance over time, which is lt minus 1. Since acceleration is velocity over time, that means the dimension of acceleration is going to be lt minus 2. So that means the dimension of force now is now going to be m, that is the dimension of mass. Now don't forget, acceleration is still derived quantity. We have to simplify it further until we get derived fundamental quantities, which is distance over time squared, and distance is L, then time is t. That's why we have lt minus 2. So the dimension of force is now going to be mlt minus 2. Now for you to know if you are right, m simplify mass, L talks about distance, t talk about time. So since acceleration is velocity over time, where velocity is also displacement over time, so displacement is representing the L. Now that means acceleration is the same thing as displacement over time squared. So displacement is L times, then we have this minus 2 because we have length over t. So that's for this. Now let's go to the second one. The second one is momentum. And don't forget that the momentum is a product of mass and velocity. Now don't forget that velocity itself, velocity is displacement over time. So since velocity is displacement over time, that means the dimension of velocity is going to be L over T, and the dimension of mass is m. So that means the dimension of momentum P is now going to be dimension of mass multiplied by dimension of velocity, which is LT minus 1. So MLT minus 1 is the dimension of momentum. Now let's go to the third one, which is Young modulus. And don't forget, in my video, if you have watched about Young modulus, you should know that Young modulus is stress over strain. If you don't know that, you can check my previous video, and where your stress is force over area, your strain is extension over length. So now let's go to the other side of the page. Now don't forget that we already know the dimension for force. So force is MLT minus 2. So what of area? Area is length times breadth, right? And that's going to be m. That's going to be length times breadth, and don't forget length is L. So breadth is also a measure of how long something is. So we have L squared. Are we together? So we can now say stress, which is force over area, is now going to be MLT minus 2 over L squared. And at the end of the day, we are going to have stress to be equals to ML. If you perform indices here, you can watch my video on indices. It is going to be minus 1 T minus 2. So this is dimension of stress. And don't forget strain, which is extension over length. Don't forget this one is unitless, because you are going to have L over L, and that's going to be 1. So since Young modulus is stress over strain, that means Young modulus is going to have the dimension of strain, which is ML minus 1 T minus 2. Now for the last one, which is gravitational constant, if you remember, F equals to G M1 M2 over R square. That means our G is going to be F R square over M1 M2. Make G the subject of the formula since we are looking for the dimension of G. And recall, the dimension of force is MLT minus 2. We have solved that before. Dimension of mass is kg, right? The dimension of radius, we're just talking about distance, so that's going to be L. So the dimension of R square, which is radius square, is going to be L square. So we can say G, gravitational constant, is going to be MLT minus 2 dot, what is our R square? That's L square. Then product of two masses, that is M squared. So that means our G, if you perform your indices, this is going to be M1 minus 2 L3 T minus 2. So the gravitational constant is going to have a dimension of M minus 1 L3 T minus 2. So this is the dimension of gravitational constant. This is the dimension of Young modulus. This is the dimension of momentum, and this is the dimension of force. So thank you for watching. See you in the next video. Bye.